right? And today is October 5, 2024. So last time we were talking about various latches and flip-flops, right? So this is what we are talking about. So latches are the one which are having the label sensitive clock. Flip-flop is the one which has age triggered clock. Right? And we talked about RS latch. And we also learned that RS latch uses this memory element over here, right? And we have applied here, the R and S. R stands for reset. R for reset means Q will become 0, and of course Q bar will be 1 at that time. When set will be 1 and other counterpart is 0, then Q equal to 1 and Q bar equal to 0. In this case, when both are 0, R and S both are equal to 0, then Q and Q bar are going equal, and this is the alarming time. We should not consider this, and we should declare that one as an invalid state, right? So this is what we studied, right? And we also added one more gate before that, with enable signal. Later on, enable have been changed to clock, right? So that is what we have studied, and accordingly you are giving the input. Note that the truth table. Okay, so various things I need to say in the case. Truth table is applicable for generally for all combinational circuits. For sequential circuits, it's a state table. For flip-flop or latch, if you are writing any such table, it is known as characteristic table. And if you are writing the output in terms of input and all, those are known as function, or sometimes characteristic table or state table or truth table, all of them can be known as function table, right? So all are synonym to each other, but this is how different books are defining the things, right? But these are the popular way to define it. So here what we are saying is, if there is a characteristic table or the state table of RS latch, what we have studied might be little bit different than others depending on the situation. Which kind of gates are you using? If it is NOR based circuit, then this particular equation will be changed, right? Because it will give you the answer of 0 0 or the invalid state when both the inputs are 1. When these are NAND gates, in NAND gates it changes and it will latch the previous one when both are 1, right? So in book they are using NOR, we are using NAND, okay? So please be careful about that. However, whole philosophy remains same, what we talked about, reset and set. So 0 and 1, 1 and 0, if they are there, then accordingly the output will change. However, in the case of 0 0 and 1 1, you might have different, the truth, the state table, right? Okay, so we talked about this. Okay, and we also studied about the D flip-flop, right, or the D latch, where we have added one more gate over here. which makes sure that two inputs are not going to become same ever, right? So this is what we studied. In this case, qt plus 1 is equal to d only, that is what we also derived. Now let's go to the next part, which is actually a JK latch. It's very popular. This was invented with the same fact that they don't want invalid output. So to get rid of invalid output, JK was invented along with D latch. D is very simple, but JK is a bit, I don't say very complicated, but little bit tricky to understand. So book is using this circuit, but we are using NAND based only, because that is the one which is used most of the places. Whenever you go to the industry, you will see that this is the circuit which is used. So everything is NAND based. So I am also using same thing. The only difference over here is it's similar to what we studied. There is actually two more feedback, which makes this a bit tricky, right? So here let's start with different inputs and how it works. Let's see that, right? So there are three inputs, as we know, qt, j and k, and output is qt plus 1. So there are 8 possibilities. Okay. So in this, let's start with the first one. When both are 0, then what's going to happen? When both are 0, I am feeding here, both are 0. If both are 0, then there is no problem. Look, output is 1 1 at the output of first and second NAND gate. Output is 1 1, right? So what should be the output over here? What do you think? If both the inputs are 1 1 in such configuration, output has to be latched to the previous value. Let's see that. What I mean is, if q of t is equal to 0, I am expecting that after settling the whole thing, I should get 0 only. It should not change, right? So let's see. So 0 is coming here back, and 1, which was q bar, is going other side. So it will not change this 1 1 because 0 was already there, right? So it will remain 0 only, and this will remain as 1, right? And it will not change. If you flip that, then also it's same thing. If you flip the q and q bar, which we have chosen, instead of that, if you are taking this one, then also the output of the first stage is 1 and 1 only, right? Because it's not depending on q and q bar. And if you go further, you will see that it remains staying there wherever it was. So it's actually q of t, or you can write it down 0, and here again 1. It's actually q of t. Do you agree with this one? Right? Now let's look at the case when 0 and 1 and 1 and 0. One of them has to be set and one of them has to be reset. So let's see which one is setting and which one is resetting the things, right? Again, it will not depend on q of t. That should be the answer. Let's see whether it's giving similar thing or not. So if j equal to 0 and k equal to 1, and here q of t equal to 0, then this 0 is coming here. Output of this one is 1. Here it's 1. And note that phi is equal to always 1. That is what we agreed, because it's a level sensitive latch. So it will require this input to be 1 for forever, right? And if you don't, if you want to latch it, then you give 0. right, because that will give me here 1 and 1, so it will not change the output at all. So if it is 1, then this one is 1 and this one is again 1, right. So if this is 1 1, this 0 is coming here, this will make 1 and this 1 is going here, so 1 and 1 makes 0. So this becomes 0. You see, we have to read this one as K as reset and J as set. Maybe with time you will understand. So if it is 1 0, then what's going to happen? Let's look at that. It has to be reverse 1. And if this Q equal to 0 and this equal to 1, then other side will be 1, this is 1 and this will become 1, this will become 0, this is 1. So 1 and 0 will give me 1, right, and this 1 will go there, so it will make 1, right. Again it has to, okay, at the beginning I made a mistake to take it 1, but still it will not change this output, but 1 will be coming here, still it will be same, but thus this one, okay, let me check this loop again, I made a mistake, let me see. Okay, so J equal to 1, K equal to 0 and Q equal to 0 and this equal to 1. So 0 is coming here, so it has to be 1 and 1 has to go that side, so it has to be 0, right. So any input is 0, so output has to become 1 and this 1 will be coming here, so this will become 0, right. And you can see, you can check for the rest of the cycles also, this 0 will go here, this will become 1, this 1 is coming here, this will become again 1, so it will latch the previous thing, means 1 and 0. So this will become 1 again, means J equal to set. Is it okay? Or so let's check same thing with other input, which is Q equal to 1 and Q bar equal to 0, J and K are 1 and 0. In this case, Q equal to 1, so this will be 1 again. Let me remove all these things because it will create lots of problem. Okay, so this will give me 1. Here this is 0, so it's going 0, so this will again give me 1. So this will 1 and this will be 0 because both are 1, right. If you look at for the stable output, you will again see that for the set J you will have 1, for the reset K you will have 0, right. Is it okay, or do you need to get another explanation on this? These are fine or not fine? Vidhan, any? Which one? Fifth one, this one. Okay. So J and K both are 0, right, and Q equal to 1 you are saying, so this has to be 0. Both the output has to be 1 because both are 0. It will not change this position at all as both are 1 1, right. Both are 1 1, then it's not going to change it, right. And simultaneously J and K both are 0, so this will be 1. It is not depending on the another feedback which is coming from the second stage, so it will be always same, so it's Q of t. Okay, other than 4th and 8, any doubt? 4 and 8 we haven't done it, it's a different one, it requires like understanding. So any this is fine? Okay, so if this is fine, let's look at this condition because that is very important condition. It has also some name, so we will talk about it, but before giving name to that, let's understand how it works. So if q of t equal to 0 and this equal to 1, so 0 is coming here, so 1 0 will give me 1, this 1 is going here, so all 1 will be 0. Do you agree with this one? Any input is 0, for the third NAND gate output has to be 1, 1 should be coming here, output becomes 0, this has become flipped. In the next instance this become 1 and this becomes 0, because of that this become 1 and this becomes 0, because of 0 this become 1 and this become 0, right. So if you draw the output, you might see that you will have this kind of diagram at the output when both j and k are 1, but this is the case when it's NAND gate. That will be different if you are using NOR, then it will be for 0 0, right, or if you are using the circuit which is like this, it will have different condition. You need to find it out, but I am talking about both with the NAND gates, because NAND gates are the popular one everywhere, all the flip-flops, everything which are inside, they are using NAND gates, that is why we are using this. So they are going to give you non-stable output or the unstable output, it is always oscillating. Can we find out the frequency of this oscillation? What should be the frequency of this oscillation? 3 of propagation delay of NAND gate, right. So that will be the oscillation frequency, right. Moreover, this particular condition is known as the race around condition, by the way. It's very popular. Sometimes some people are using this flip-flop to create oscillations of their desired frequency. What 3 of 3? These two are in parallel, right? You just tell me. So it's again when it's coming back, both are processing in parallel, right? It's not going in serially. They are in parallel. NAND gate 1 and 2 are processed independently. Their inputs are not actually given like one to another one, right? That's why it's only one. So on critical path, either 134 or maybe 243 will be there, right? So that is what I was saying. Sometimes people are using this circuit to make an oscillator which will oscillate between 1 and 0 for the desired frequency, but they need to control propagation delay of these NAND gates very carefully. So this was the thing. If you change it to other way around also, then also like if it is 1 and if this is 0, then also situation will be same and it will flip to 0, then 1, 0 and so on and so forth, right. In this case you can write down that here what we are getting is actually q bar of t. Whatever q is there, next instance you should get 1, afterwards 0 and so on and so forth. Same is for here, right. So you can write down that it's actually q bar and q bar in both the cases when both are 1. Both are 0, then it's q of t, right. Now any doubt in this one? JK latch, okay. So if no doubt, then maybe we can write down the characteristic equation using the given truth table. Here you can see in the book they are taking 1 to 0, when both are 1 1 it's q bar, both are 1 1 it's q bar, both are 0 0 it's q of t. So here it's q of t, here it's q bar of t, here q of t, q bar of t, and in the case of this one, this is set and this is reset. When set equal to 1, my q of t has to be 1, and when reset equal to 1, q of t has to be 0, right. So that is what kept it over here, and accordingly this truth table, the K map has been made and this equation has been found out. So it's little bit, yeah.
In the book, the NOR gate is used.
Sorry.
In the book, the NOR gate is used. So for the first condition, it should be.
So that's why like they change this location of K and J. My location of J and K was different. Right. Right. So truth table generally remains same. For RS latch, it's changed. RS latch is the one which is changing the truth table, right? So that you need to check. Okay. The characteristic equation over here, J cube prime plus K prime Q. That was the equation for Q t plus 1. So generally like the most popular flip flop or the latch is the D. So it's simpler one, or you can say that that is available in the library or any design block. So what people are doing, they are using the D and they are deriving other flip flops. So they are using actually D, they are not using J, K and others, but they are using D. So in that case you need to derive all different flip flops using D flip flop. So that is what I kept it over here, that if this is the equation and this is going to be the output, I know that D works as follows, that Q of t plus 1 is equal to D, because after some delay of 3 propagation delay of NAND, you will get the answer, right. So you can say that it's following the D after delay. So it's actually the transparent thing after settling output, or it's as good as a buffer. So if this is the case, I can feed over here this equation, which is J and Q prime plus K prime and Q, both will be getting odd, and if it is fed to the D, then same will be output, but it will add extra additional delay. In this whole process, delays will be added, that one needs to understand, right, because earlier JK has some 3 propagation delay of NAND, but now it's actually more. That needs to be taken into account. Here actually the on critical path, these things will also come, right, that needs to be added. Anyway, now there is another one which is very popularly known as toggle latch, or same for toggle flip flop. Toggle latch is the one which is going to give you the toggling output, means it's 1 and 0, 1 and 0. By the way, because of toggling nature of the output, this is known as T latch, right. So if I want that, how to get it, right. So if J and K both are 1, if inside that NAND gate based configuration is there and clock equal to 1, if all 3 are 1, output will be, do you agree with this one, right. So this is the case for this one, but if I want to make it with D flip flop or D latch, I want to get the output which is toggling one. How to get that? Generally D is the one which is giving you same output. D is equal to QT plus 1. So what I am doing, I am adding one XOR gate over here and giving one input T and connecting to the output. T will be 1. When I am doing this, at the first instance this might be 0. Let us assume that the output is 0. So then 0 is going to be fed back, this will become 1. 1 will be available at the output after some time, that 1 will be fed back, 1 plus 1 will be 0, 0 will be fed back, it will come here. So the output will be oscillating or the toggling all the time, and its frequency of toggling is depending on now 3 propagation delay of NAND plus propagation delay of XOR, right, because XOR is actually in the loop, that has to be taken into account, right. So this is the theory of this different flip-flops. Now let's revisit all the state table which we have studied till now, because I am going to derive something very useful which will be useful in designing a logic circuit where the some statement will be given to you, you have to find out its logical circuit, or you need to find out the hardware. Let's assume that you want to design an elevator circuit where different inputs are going. So somebody is giving the input from outside, right, outside the lift. Inside elevator you also have multiple inputs, right, 1 2 3 4, all these inputs are there. So you have to design a circuit which will give signal to the elevator that it has to go up, down, where it has to stop. So this is a very simplest example. Same way like the traffic light signal, all these things where you need to give some sequence of things, then you need to draw something called excitation table. So that we are going to study, but before going to that, let's look at the RS latch. How does it look like? RS latch is the one which has 3 inputs, right. So 0 0, I am talking for NAND based RS latch where 2 inputs are 0 0. What output I am expecting? It's an invalid, right, because both the outputs are 1. If it is 1, irrespective of what QT is there, we do not care, whatever QT is there, output is equal to 1, right, Q of T plus 1 equal to 1. If you look at 1 0, whatever Q of T is there, the output is 0. But in a case of 1 1, Q of T will be transferred at the output, right. So this is what we studied. Now this particular equation is known as or table is known as the state table or the characteristic table. I want to find out the excitation table which will be fed to those circuit diagram. So excitation table is the one where there are inputs which are present state and next state. Based on this you need to find out inputs. So you know that what will be the present state and what will be the next state. Based on that you need to find out inputs which are RNS in this case. So you derived QT plus 1 based on the inputs RNS, but now excitation table is the one where we are going to have one side present state which is Q of T and the next state which is QT plus 1, and you need to find out possible values of RNS. Okay. So if both are 0, so refer to the table which is on top if both are 0. Can we say that this particular situation when both are 0, right? Because this is don't care. I can consider this one as 0. So 0 0 will give me 1 0. So output is 1 0. Any other condition where such things are happening? 0 0. Fourth row is also giving you 0 0, right? Because both are q of t. So in this case, just I am taking those things aside. One is don't care 0 and another one is q of t, fourth row, where one is 1 0 RNS and another one is 1 1. So whichever is actually changing, you can call that one as don't care, or you can say that if the inputs are 1 and don't care, then you will get the output 0 0, present state 0 and the next state also 0, right? In another way around we can say same thing. So if both are 0, we can write down it's 1 don't care, right? Again I am saying this is derived for NAND based latch. In book it's derived for NOR based latch, so you will get the answer 0 don't care. Okay, so do not get confused with that. If it is now 0 and 1, now find out where it become 0 and 1. So it become 0 and 1. I am not considering, by the way, invalid state. We don't like invalid, so we will neglect that. So 0 1 is only happening at this place. Do you agree with this one? Right? There is no possibility in these three other possibilities where that will happen. So for that we will have RNS value as 0 and 1. For 1 and 0, that will be the case. So you are going to have 1 and 0, and when both are 1, then this is also possible. Let's make it, this is also possible and this is also possible, right? Right, because this is don't care, so you can consider that one as 1 and this one is 1. Q of t you can consider as 1, so both will be 1. So you can write down here as don't care 1. Is it okay or no? Okay. Okay, so let's start from beginning. 0 0. So where is the 0 0? Yeah. Tell me, where is 0 0? First one is the invalid, and you are looking at RNS. You have to look at Q of t and Q of t plus 1. You have to observe Q of t and Q of t plus 1. Sorry, I should have made. You have to observe these two things. Look at that, these two are the columns here, not RNS. You need to derive RNS. So if both are 0, so where you are saying both are 0? Third row. What about fourth? Fourth row is Q of t. I can consider that one as 0 also, right? If Q of t equal to 0, then fourth row will also be there, which is going to give me this combination. But in that case, I am getting two things, 1 0 and 1 1. Whichever value of the input is changing, like a K-map, just you make that as don't care, right? Because it's not contributing anything. Any value you are keeping, it will give the same answer. So we can call that one as don't care. So 1 don't care, that will be here, right? Now let's look at the next one, which is 0 1. So can you tell me where is 0 1 is happening? Where is it happening? 0 1. Second one, right? There is no other possibility. I cannot take it because both are Q of t. Here it's maybe 0 0 is possible, 1 0 is possible, not 0 1. So 0 1 is happening here. So as it is same thing, you can write it down here. For the case of 1 0, you can write down here 1 0. For the case of 1 1, I need to consider this row and this row, right? So both will give me that. So it will give me don't care 1, right? Can we try for, let's say, JK? You just keep this table somewhere, okay, in your notebook. So if 0 0 1 don't care, 0 1 0 1 it's same actually. This is same, and this one is going don't care 1 and 1 don't care. Now let's talk about JK. So how JK works? What was the characteristic equation over there? So let's look at that. Right. So Q of t plus 1 in case of 0 0, what was the answer? I am expecting to have the Q of t, right, in the case of 0 0. But in the case of 1 1, what was the answer? Q bar of t, right? Although it is checked only at DC, however, if you are checking at the further on transient, you will see that it's changing 1 0 1 0, right? We have to read J as set and K as reset. When set equal to 1, output is 1, means Q of t plus 1, and irrespective of whatever Q of t you are keeping, it's not depending on Q of t, but it's depending on only and only J and K inputs. So reset is there, so it will be 0, and set is there, so this will be 1. Do you agree with this one? This is the same thing which we have studied, right? So in that case, can we write down the excitation table? What excitation table says? The inputs are Q of t plus 1, and other sides are output are inputs, right? Right. So if those are 0 0, yes gentlemen, that guy, I forgot his name. Yeah. What's your name? Vedang. So Vedang, tell me, if both are 0, then what will be the inputs, J and K? Second one, which one? If Q of t, so here also Q of t, here also Q of t. So we have two possibilities. Can you see? This and this. So what will be the answer? What should I write here? 0, don't care, right? If 0 1 is there, then what should I write? 0 1. In that case, can I consider this one and this one, right? 0 1. If Q equal to 0, then Q bar become 1. So this is 0 1 possibility. This is again 0 1. So in that case, what I can write down? 1 don't care. Let's check about 1 0 and tell me the answer. 1 0. So 1 0 is happening over here and here. So what we can write down? Don't care 1. And for the case of 1 1, for the case of 1 1, don't care? No, then. Okay. Just for sanity check, you will never have such kind of output. Don't care, right? Then there is no use of logic at all, right? Okay. So this is the one. If I am writing about D flip flop or D latch, by the way, one important thing, all these tables, all these things remain same for latch and flip flop. They are not changing. Okay, they are changing the nature or giving the output over the time, right? If you are having the latch, then it's going to give you the output on the basis of level of the clock. When clock is 1, then the output is available. In the case of flip flop, when clock is transitioning from either 1 to 0 or 0 to 1, it has to be defined from your flip flop whether it's positive age triggered or a negative age triggered. Accordingly, you will have the output in the transition only. Okay. So that is the whole thing. We know that Qt plus 1 right? Qt plus 1 is equal to D after some delay. So then we can write down same thing, right? Here only one input is there, so I can replace this D with Qt plus 1, right? Just I have to copy the next state to the D. That is the only thing. But in a case of T flip flop or T latch, it has to be, right? Because it's complementary of Qt plus 1, or maybe you can say, yeah, it's complementary of Qt plus 1, right? So that is what is going to happen. That's what you can write it down. So these are the excitation table for all four flip flop and latches we studied. But now the important part which we need to understand before going into anything, okay, is actually flip flop. So as I told you, like all the flip flops are derived from D flip flop only. So if you understand D flip flop, then other flip flops are going to be derived from that. So that's why we are studying only D flip flop. In book also, all the books, they are only having D flip flop. However, you can design JK flip flop also separately if you wish, but that's generally people are studying at the advanced level, right? But at this stage you don't require, but if you want to derive it, you can derive it. It's not so much difficult, even though people are studying at the advanced level, but they are very simple one, right? So what exactly we are doing here is, we are having 3 memory elements like this. Rutul is here. Rutul. Okay. Priyal is also there. Okay. Can you get that? Okay. So we can have one surprise quiz, right? So today we have 2 surprise quizzes together, right? Yeah, because we missed one last time, so right. So at least you can. That will be the one which we have studied. It's not from the future. Okay. Nothing is given from the future. Okay. It's not Qt plus 1. It's from the previous state, which is Qt, right? Whatever you have studied. Okay. So it's very simple, by the way. Everybody can score 10 out of 10 very easily. There is no problem. Okay. So let's study this. Okay. Before moving to the surprise quiz, let's look at this. It's very simple. That quiz is simple. Okay. So let's assume for the given structure. Excuse me. Hello. So for the given structure, if clock equal to 0, then what's going to happen? Look at this. There are 3 memory elements, right, which we have studied at the beginning. If you remember, and you remember the characteristic of that these memory elements also, that whenever both the inputs are 0, it's going to give you the invalid output. If both the inputs are 1, it's going to latch the previous output, and set equal to 1 means output is equal to 1. If reset equal to 1, output equal to 0, right? This is the characteristic of this memory element, right? If both 0, invalid. If reset equal to 1, set equal to 0, Q of t plus 1 equal to 0, reset equal to 0, set equal to 1, Q of t plus 1 equal to 1, and if both 1, then it will latch, or it will remember the previous state, right? So that is what we studied. Let's keep this in mind while solving this particular structure. So if clock equal to 0, irrespective of what is output, the input S and R will be 1, right? Doesn't matter what you are giving other things, both will be 1. If both are 1, and this is open loop system, so this Qt plus 1 has to be the previous one. Whatever you have assumed, same will be here. If it is 0, right? So if it is clock is 0, this is what going to happen, that it will latch the previous state. If you want to check, you need to give some input. Let's give some input let's say 0. If I am giving 0, this will become 1. If this is 1, so then this will be 1, this will be 1, and this will give me 0. This is 0, so this is 1, right? And if this is, if I am assuming some q equal to 0 and this equal to 1, then this is 1 and this is 0 forever, not changing, right? You can check for other things also, right? If I am changing this D input from 0 to 1, now keeping all the previous condition as it is, right? It's actually stored. If you are not power it down, all these ones and zeros will be stored as it is. Now I am changing this D from 0 to 1. Let's give that from, if it is going from 0 to 1, then what's going to happen? This one and this one is going to give me 0, right? This 0 is going here, so it's already 1, so it's not going to change, right? So it's again remain 1 only. This 0 is going up, so this will make 1. Even though it is 1, output will remain 1 because of the clock input, which is 0. So in between 0, whatever you are doing, it's not going to change anything, it will latch the previous state. But what will happen if, let's keep all these values as it is, whatever we got it. So whatever value we got it, let's keep them as it is. I'm keeping it in green color so that we can identify that. Now if we are changing this to 0 to 1, right, because that is most important over here, then what's going to happen? If it is going from 0 to 1, then this is 1, this is 1, so 1 and 1 will make it 0, this coming 0, so this will become 1, this 1 goes here, 1 and 1 will make it 0, this 0, right? This 0 go up, this make 1, 1 and 1 again 0, right? For 0 and 1, if it is reset equal to 1, I should see q equal to 0 and this equal to 1, right? So I am not deriving it as it is very simpler one. Any input is 0, so output is going, 1, 0. Here again it's a mistake of, I should call this one as reset and this one is set. Okay, this is actually the problem with the book. So I should call this one as reset and this is set. So set equal to 1, because of that this become 1 and this becomes 0, right? So you can see going from 0 to 1 is actually taking this D as output, because this is what we were expecting, right? We are expecting that q of t plus 1 equal to D when clock is moving from 0 to 1, right? Now what if I am not changing this one, and if I change, okay, before going to that, let's change this 1 to 0. Okay, so we also learned that in flip flop, if this is a clock and if this is a D input, I'm not drawing ahead, but so here if it is latch q t plus 1, then the output has to be exactly identical to D, right? But in a case of flip flop, q t plus 1 has to be this one only, and afterwards it becomes 0. Can you see at the transition? So at the transition, whatever the value is there, that will stay there. At the transition, this was 1, that's why 1 is coming here. At the transition of this one, 0 is there, so 0 has to be there. So that we need to check whether it's giving the same thing or not. So if we are changing from, let's say 0 to 1 we made it, if we are making that, so in between if we are changing anything like from 1 to 0, what will happen, right? If I am changing D from 1 to 0 by keeping other conditions here, we can't change it, right? Until it's getting power off, it will stay there and it will run as per the understanding. So if it is going from 1 to 0, what will happen? This will become 1, this 1 will be here. Even though this is 1, it doesn't matter, this 1 will give you 1 only, right? This blue color is running right now and still this is 1 because 0 is here, okay. And this one is going up and this was already 0, so still it is 1, this is still 1, 1 and 1 is going to give me 0 and still it is 0 and 1. So input of this one, which is blue colored, remains 0 and 1, so still Q remain 1 and Q bar remain 0. It's not changing with respect to D. That is what expected in a D flip flop, get the answer. But you need to keep those conditions intact. You can't change it. If you are changing, then the whole game is over, right? Then you have to wait for some propagation delay, right? Same way if you do this, I am keeping this to you people, check that going from 1 to 0, output should not change. Of course it will not change because this will latch, R and S will equal to 1. Irrespective of whatever you are feeding here and there, this becomes 0, this becomes 0. So output of R and S will be 1, 1 only. So it will latch previous thing and it will give you the output only when there is, okay, where is that? So output will be there only when there is a transition. Afterwards nothing will happen. So the two useful phenomena over here is setup time and hold time. So I'll talk about it, maybe I'll again I'll talk about it in next lecture also, but these two are very important. Just consider this clock as a clock as a train. If train is there on, let's say on Sabarmati platform, you have to be there on time, right? So what is expected from you? You are the input. This is a train. If it is scheduled at 9 AM, what is expected? What is expected? You should be there at 9 o'clock or before 9 o'clock you should be sitting inside. So this D input has to be available. So this whatever I drew right now, it's an ideal condition. This will never work. You have to be before time. So this time, and look, if train is started and if you get down, then you will not going anywhere. You are on platform only. So in that case you have to be seated in the train or until TT is not coming and checking your ticket, right? Till that time you have to be there. If you are there, even though you will be get down, your name will be there on the chart, right? That is the meaning of that. So same thing is happening here. Even though somebody has get down, he wants to go to Delhi, but he get down at Jaipur, but still as per our record, it's like he is going at Delhi only, right? So this particular situation is known as, so before time, whenever you are sitting there, it's known as the setup time, and you are sitting inside the train, it's actually the whole time after. So some small window will be given depending on how you are designing inside these gates are known as are depending on the setup time and hold time, and you should not violate that. If you are violating, means your answer will be different than what you are expecting, right?